Hi, my name is Emma Bateman, and today I'm going to be doing the physics of a vacuum cleaner. And so first we need to understand the basics of pressure and Bernoulli's principle. And so I'm going to be explaining that on my iPad. Should I switch over now? And so first I'm going to be starting off with pressure. So come in here. So first I always start off with more of like a visual kind of understanding, and then I'll go into the definition. And so pressure, as an example, we can start off with a deflated balloon. I'll probably spell something wrong, just so you guys know. Okay, so we're gonna have a deflated balloon, and what we do to an inflated balloon was that we want to inflate it by blowing air into it. And so whenever that happens, it then, as we all know, it becomes inflated or bigger. And so if we take a little section of the balloon, we can then look at the gas particles outside of the balloon and then the gas particles inside the balloon. And they're all going to be moving in a random direction because that's what gases do. And so they're going to have a very small mass and they're going to have some velocity to them. And so whenever that happens, it hits into the side of the balloon, bounces off, and exerts some force that is perpendicular to the surface of the balloon. And so these particles on the outside are going to be exerting another force on the outside. And these need to be constant once you inflate the balloon, because the balloon is not accelerating outward or inward. And so now it is time to define pressure. And so pressure is going to be the force that all these particles apply on a given area. So here's like some area, and it's the force that is getting applied from the gas particles. And so we need to ask ourselves the question, why does the balloon expand? And so the balloon expands because what is happening as we put more gas particles into the balloon, the force of the amount of gas particles on the balloon increases. And so we then need to increase the area of the balloon. And specifically, it's the surface area on the outside. So that's why the surface area starts really small and then it expands much greater. And so one key principle of why it wants to do this is because pressure always seeks equilibrium. And so this is a very, 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 very key principle of pressure in fluids. And so to summarize this, we have a given area, and whatever force that is applied on the given area can be described as pressure being the force distributed over the area. And so the somewhat formal definition of pressure is the force distributed over an area. Okay, so now that we understand pressure, we now need to talk about Daniel Bernoulli. So Daniel Bernoulli, well, he was a Swiss mathematician and physicist from the 1700s, and he kind of wore one of those like funky little wigs you always see in the history textbooks. And so we're first going to be understanding the Bernoulli's effect, which is more of a visual concept that we can talk about, and then we'll go into understanding the Bernoulli's principle. So first is Bernoulli's effect. So Bernoulli's effect, we're going to have two different situations. And so we're going to have the same sheet of metal here. And oops, that does not look like. Oh, I'll just copy it over. So we're going to have gas particles randomly scattered above, okay, the sheet of metal. And the sheet of metal is just laying on the table, just for reference. And so with that, all these are going to have random motion because it's just going about in the air. And so given area, and then this is the given force. And because it's just laying on the table, we usually denote this force over the area as being the atmospheric pressure, because this is the pressure that we feel from the atmosphere. And so this is a very constant number that we usually see and use in real life. So from that, we now need to have our second situation, and we're going to take the guy Bernoulli, put him over here, and what he's going to be doing is, well, he's going to be blowing, and he's going to be blowing in the rightward direction. And what's going to happen is now the particles are going to be kind of going mostly towards the right. And so the difference between these two situations is that in this situation, the air particles are, well, they're going to be going faster for one, so the velocity is going to increase. And then whenever that happens, they're also going to be going in a uniform direction, which is actually specifically parallel to the surface of this metal. So the sheet of metal is laying like this, and then the air molecules are going to be going to the right this way. And so whenever that happens, because the air molecules aren't randomly going, they're going in one direction, they're actually less likely to hit the sheet of metal. And so the pressure in this situation is actually going to be different from that situation. And so because this happens, the force decreases, which then causes the pressure to decrease because the area is constant this time. In our last example with the balloon, the area was changing, but now we can see that the pressure can actually change. And so we can say in the second situation, P, so this P is going to be less than the atmospheric pressure. Okay, so now that we understand that, now we can go into the quantitative Bernoulli's principle. And so this was kind of like the understanding, the qualitative understanding of what Bernoulli did. So now we can now go into exactly what did he define. So this is Bernoulli's principle. And he got here basically by understanding that there's this conservation of an energy density. And so this is just kind of like the way that he thought about it. And so earlier in the year, we learned about energy conservation, but now this is energy density conservation. And so so we can have a situation that is going to always be constant to the other situation. And so we're going to have the first pressure plus also this Greek symbol. This is just density, and it's the density of the fluid. So that's important to keep in mind. So this is going to be density, and then this is going to be times the velocity squared plus the density, almost like the gravitational energy. And so that's going to be then constant to the second pressure plus 1/2 the density, second velocity plus the density, the gravitational times that. And so what we can see here is that we know that pressure is force over area. And so we can kind of think of it as an energy distribution, which is like over an area. And then if we times the velocity times the density, that's kind of an energy density of kinetic energy. And then the other one is the gravitational potential energy density. And so this is always going to be a good tool to use. And so if we use it in Bernoulli's effect, my example that we gave us, what we said was in the second situation, the velocity increased, which then made the pressure decrease. And so that's specifically for this one. And so we can apply Bernoulli's principle to many applications that we can see in the real world. Okay, so now I'm going to talk about vacuum cleaners. And so first I'm going to be drawing kind of like the structure of the vacuum cleaner so then we can understand what is exactly happening in the vacuum cleaner. Okay, so vacuum cleaners, hopefully I'll use one. So now I'm going to draw it with the knowledge. Well, this is just basic knowledge of just kind of what it looks like. And so it kind of has a tube and then it kind of has the suction part. And so on the inside, there is actually a fan. And you have a little vent. And so this is just kind of a simplified version of a vacuum cleaner. Now, ours today are a lot more complicated, in my opinion. And so what happens is once the fan gets powered on and you turn on the vacuum cleaner, it starts moving the air in this direction. And as we all know, whenever we increase the velocity of the fluid, which is the air, then that is going to be lessen the pressure that it was originally at, which is the atmospheric pressure, which is on the outside of the vacuum. Okay, so now this air is going to be getting pushed out of that vacuum, but then the vacuum cleaner wants to, well, not the vacuum cleaner specifically, it's the pressure concept. It wants to have an equilibrium, which is then going to be trying to suck up the air. It kind of creates this endless cycle because you always have this fan pulling the particles in one direction, which is out the vacuum cleaner. And so if we look, and if we place it on a floor like this, and we take a closer look, we're going to have a vacuum cleaner here. And then on top of it, this is going to be the atmospheric pressure. And so this is going to have a lot of force compared to the underneath side, which is going to have less because you're kind of sticking it to the floor. And so it's going to be trying to pull everything up. And so let's say we kind of have our carpet here. And in the carpet, we have the gross, and we got hair, we have dirt, we have all the nastiness. Okay. And so what's going to happen is the air almost sweeps up under here, kind of grabs these gross dirt particles and kind of pulls them up with it. And so it takes the atmospheric pressure and like pulls the air from the top all the way under here because it's trying to get to an equilibrium. And so all the air is going to be carrying these hair and all the gross stuff all the way through the vacuum cleaner until it reaches a bag where it collects all the dust and the dirt. And so this is just kind of how a vacuum cleaner works in general. And also a word that we always use that we should define is suction. So suction is actually just the force created when there's an air pressure difference. So if you've ever tried to like stick the hose to your hand and you see that there's like the suction to it, it's just a force that's created because there's an air pressure difference. Now, this only works because pressure always seeks equilibrium. Okay, so now I've explained the vacuum cleaners and the knowledge that you need to know to understand the vacuum cleaner. I'm now going to be explaining kind of how the implications of this. So if I go back to my slides, so the connection that I made during class is, well, the topic was pressure and fluid dynamics, and so that's very applicable to vacuum cleaners and everyday household items which we talked about in class, like straws or suction cups. And so what you need to understand to make this connection is you need to understand the pressure principles and exactly what is pressure, and also understanding the Bernoulli's effect or M principle. And so the relevance of understanding this is that it's very important to understand how these items that we use every day work. And the reason why it's important is not only to understand what we're using, but also to figure out ways to fix it or make it better. And so whenever your vacuum cleaner breaks, you can now figure out, well, is it just not picking up enough dirt, or is it actually broken? Is there some other issue? And so I remember I was in elementary school and my vacuum cleaner wasn't sucking up as much. And so the vacuum cleaner would turn on, but there's very little suction. And so if you know that there's very little suction, that means that the pressure difference is not great enough. And so basically you're having the pressure inside the vacuum be higher than what it's supposed to be, which is closer to the atmospheric pressure on the outside. And so there's kind of like there's a lot of different reasons for this. And so you can check if the fan is spinning fast enough. Like, do you need to change the batteries? Is it not getting plugged in correctly? Things like that. Or you can even see is it inside of your vacuum, not where the bag is at, but the actual inside of the parts. Do they get dirty with like dog hair and dirt and things like that, which can be slowing the fan down. And so that was in case that was what was happening to my vacuum, was that we actually had to clean the parts of the vacuum, not just empty the bag. And so that's kind of how we can understand what happens if something breaks like a vacuum cleaner. And then another thing is that it's very important to understand how these work because you can also make it better. And so my vacuum cleaner that I have here at college, it actually has different settings on it where you can say if it's a hardwood floor or carpet or a rug. And so you can imagine like a thick rug, you need a lot more suction to get, you need a lot more like force to bring those particles up from underneath because a carpet has a lot of little hairs, I guess. And so you need like a lot more force to bring the particle up from underneath it. And whereas on a hardwood floor, it's very flat. And so you don't actually need that much suction to bring the particles up because it's like closer. And so it's very important to understand how this works because if it breaks, you can fix it or try to understand why it's broken, but also you can see how to make it better. And so innovations like different settings on your vacuum can make a vacuum cleaner better. And so that kind of wraps up my entire project on how vacuum cleaners work. And so the works cited are these two that I used to help understand how vacuum cleaners work and Bernoulli's principle in effect. And so thank you so much for watching and have a nice day.